analyze, and there's a few interesting patterns here.
How far have you gone?
Up to 12 or 13 terms, but I have a conjecture that would imply that the sequence continues forever, but it wouldn't give me the rest of the terms. Like I have no conjectured closed form for these at all. But
And you ran it through SuperSeeker?
yes, actually I haven't run it through SuperSeeker, but I've searched for this and this, but the thing is, we noted there's some recurrences that are satisfied by every term here, but they change which recurrence is satisfied. So for each term here, we either have AI is equal to 3AI minus 1 minus 2AI minus 2, or AI is equal to 3AI minus 1 minus AI minus 2. But it doesn't seem to be any nice rule for when which one occurs. So like for here, well, the first two terms, we don't have that. This only starts for the third term. So the third term, we have twice this term, 3 times this term minus 1. So we use this recurrence. And then we have 15 minus 2. So this recurrence. And then to go from 13 to 29, 39 minus 10. So now we have to use this recurrence. And we go for long stretches of time using this recurrence, but occasionally we have to fall back on this one. Because this one is asymptotically 2 to the end, and this one is asymptotically golden ratio to the 2n.
But you say you only know it up to 14 terms.
Only know it up to 14 terms.
So what do you
but
mean?
all those terms so far satisfy one of these. And my conjecture is that if you have a sequence that works for any length, you can always apply this one to get another term that works.
It's beautiful conjecture, but you don't have much evidence. You only have 14.
I have evidence for a bunch of other sequences.
Ah.
So this sequence I don't have more evidence, but for lots of other sequences I have evidence that that rule should continue.
And there's no way of telling which of the two.
I haven't found one.
Okay.
Okay, so the greedy algorithm gave us something, but it didn't give us anything that we can prove. But it gave us a starting point. It gave us recurrences. So the first recurrence up there, you try it for a couple terms, it doesn't work. We don't get a sequence with an aperiodic bounded new sequence. In fact, like we start getting periods, we start getting prefixes that grow, and it causes problems. But what if we just apply the second recurrence? And again, we're going to build the sequence of periods, and this subtraction set is going to be one less than that. So what if we take A0 equals 1, A1 equals 2, and then AI equals 3AI minus 1 minus AI minus 2 for all I that's at least 2. Then we get a very nice sequence. We get 1, 2, 5, 13, 34, 89, 233, 610.
Fibonacci.
Yes, this is every other Fibonacci number. So AI is f of 2i plus 1. So index from 0.
The way we say is p squared.
Yes. So we get Fibonacci numbers. So now let's just plug these into a program that looks for the period and prefix. Just plug in subsets of this and try to figure out if we have an aperiodic bounded nim sequence for this. So the nim sequence for 1 has period 0, 1. For 1, 2, or sorry, we have to subtract 1 from all the terms. So the set we're considering is we don't subtract 1 from 1, but we subtract 1 from 2. So we have 1, 4, 12, 33, 88, so on. And actually, when I was originally constructing this sequence, I constructed it like this, and I was wondering if this sequence is in OAIS. Then I looked at it like, oh, it's 1 minus, so it's every other Fibonacci minus 1. I'm like, oh, maybe that's important. And it was. So the period of 1 is 0, 1. Period of 4 is 0, 1, 0, 1, 2. Period of 12 is 0, 1, 0, 1, 2, 0, 1, 0, 1, 2, 0, 1, 2. And we can define a sequence of words that gives us this pattern. However, we haven't proved this yet. This is just experimentally. We have W0 is equal to 0, 1, and Wi is equal to Wi minus 1 squared, Wi minus 2, W1, W0, 2, where by squared or by times we mean just concatenating.
So it's aperiodic?
It's aperiodic because the first one is repeating twice. And we can let W be the limit because each Wi is the prefix of the next one, so the limit's well defined. And we have that W is aperiodic. So if we can prove that W is the nim sequence for S, we will answer this question that yes, there exists a subtraction set with bounded aperiodic nim sequence, and we'll get that the upper bound is the best possible, because this thing has an upper bound of 2. So let's work towards proving that. So the first step to look at is let's analyze W and try to figure out where the zeros are. Because figuring out where the zeros are in W figures out exactly where everything else is. Where might we find the zeros in W?
How does W begin? I'm a little confused. Which end does it begin at?
We're starting, what do you mean exactly? So W0 is 0, 1. Then W1 is W0 squared 2. And then W2 is W0 squared, or is W1 squared W0 2. And you can see that pattern here.
So the beginning
The beginning of Wi is the previous term, and then the previous term is repeated again, and then the next terms are each repeated once, and then there's a 2 thrown on at the end. So now we're looking for where the zeros are in W. So we experiment, and we get a sequence. And the sequence we get is 0, 2, 5, 7, 10, 13, 15, 18, so on and so on. So we go to OAIS. This is sequence 09, 09, 09. And what is sequence 09, 09, 09? These are elements of 073869 in runs of 3 consecutive non-equal terms. So what is this sequence? This is the sequence of averages. Of sequence 2251. So what is this sequence? This is the result of swapping sequence 201, the kth term, with the kth term of sequence 1950.
And those are both nice sequences.
in the non-negative integers.
And 201 is the Wythoff game, right?
We're getting into that. So now what are these sequences? These are the lower width-off numbers, which I will define in a minute. And 1950 is the upper width-off numbers. And these partition the positive integers. But there's a conjecture. 090909 is equal to the upper width-off sequence with a 0 at the beginning. And this sequence is much better studied than this one. It's also much better understood. So I figured maybe this behavior here is not an artifact of this sequence. Maybe it's an artifact of this sequence. So we're going to proceed by looking at this sequence. But just an aside, first of all, is that this sequence, the 783869 sequence, is conjectured to equal sequence 5206, which is one of Douglas Hofstadter's sequences. This is the G sequence, G of n equals n minus G of n minus 1. And the relationship between this sequence and this sequence is known to hold between this sequence and this sequence. All right. Monkeying around with sequences aside, what are these sequences?
So these are all definitions? These are all the official definitions of the sequences?
These are all the official definitions of the sequence. These are the official definitions of the sequences in OEIS. They all refer to each other. Except these two do not refer to other sequences in their definitions. But the point is, it took all of this in order to figure out that it was actually this sequence that mattered.
So there might be some motivation for creating them.
Perhaps.
Yeah.
Well, they come up in game theory.
Yeah, which is what this is, which is why I realized, well, this might be useful. So the lower width-off sequence, it's the floor of phi times n, where phi is the golden ratio. And the upper width-off sequence is the floor of phi squared n, and these partition the positive integers.
These are BD sequences.
These are BD sequences. This is the definition of a BD sequence. It's the floor of an irrational number times n. And so we're going to define WL is equal to the set of n such that n is a lower width-off number. And WU is going to be n such that n equals 0, or n is an upper width-off number. Because we don't know that it actually is this. That's just a conjecture, but we know that it's that. And there's another property of these sequences that I was hoping to talk about a little more, but I'm almost out of time. So I'm just going to say that the lower width-off sequence, lower width-off numbers are the numbers whose Zeckendorf representations end in an even number of zeros. And then the upper ones are the ones where they end in an odd number of zeros. And there's the Zeckendorf representation. So for an integer n, it's equal to di times f I plus 2. So it's instead of representing things by powers of 10, like base 10 representation, or powers of 2, like binary representations, each of the digits is the next Fibonacci number. So we're representing it this way, and vi equals 1 implies vi minus 1 equals 0, vi plus 1 equals 0. This is one of a couple of equivalent ways to define it. You can also define it as just minimizing the sum of the di's, or greedily subtracting Fibonacci numbers until you get down to 0. These are all equivalent. Zeckendorf proved that. And we're also going to be considering one other representation, the odd index Fibonacci representation. This is instead of using all Fibonacci numbers, we just use the ones at odd indices. So this is binary sequences with no consecutive ones, that Zeckendorf was. This is ternary sequences where every 2 is followed by 1 to the m0 for some m. So that's the property that's important for these. And in terms of the odd index Fibonacci representation, it turns out that the upper width-off numbers equals a set of n such that n has odd index Fibonacci representation ending in 0, but not to 1 to the m0 for any m. So that, and this notion is actually enough to prove that these are in fact WU. So this implies that W has zeros in positions WU. So now all we need to do is prove that S has nib sequence W, and then we're done. So for that, we're going to use a few properties of these sequences, some of which are proved via Zeckendorf considerations, some of which are proved via BT sequence considerations. The first thing we're going to use is that WL is contained in WU plus S. Second thing we're going to use is that WU plus S intersect WU is empty, which together, these two things imply that WL is equal to WU plus S. And then we're also going to use a set A. So let A equal the set of n such that n has an odd index Fibonacci representation ending in 2, 1 to the m0 for some n. So it's the other guys that end in 0. We also have that A plus S intersect A is empty. So now let's quickly prove the main results. I should probably leave this here, actually. So let's just prove it here. So first, let's show that all the p positions of S are the upper width-off numbers. So for this, we're going to use induction. So clearly, position 0 is a p position, so we're good with the base case. So if n is in WU, then n minus S is not in WU for any S by those properties over there. So this implies that all moves are to n positions. which implies that n is a p position. And now if n is actually in WL, we want to prove that it's an n position. So then there exists S in S such that n minus S is in WU, also by those properties, which implies that n is an n position. So we've got the zeros where we want them. We also get the ones by Ferguson's theorem. So all that's left are the 2's. And the positions that are left happen to be that set A over there. And this follows from the fact that if n is an A, n minus S is not an A. And so we've already assumed that all the positions you can move to from A are either 0s or 1s. So this must be at least 2, and it must be at most 2 also. So this exactly matches W. So the nim sequence is W. And that's it.
Thank you for the great talk.